Ladies and gentlemen, welcome back to another live stream. So in this live stream we're going to be creating a Gltf PBR renderer in Rust using WGPU, the library WGPU, which obviously implements the web GPU API, which works on all platforms including web. Right, so first of all, a disclaimer. I'm not going to be using, honestly, AI agents in this particular video, hopefully, unless if we had some really big problem, which I don't think would happen. Otherwise, I would probably still use like just Gemini web chat or something like that, just for regular stuff. But I'll try my best to mostly code everything on my own. I have never made a PBR renderer before, at least not a full one. I did try to prototype something using AI and you know, just the regular stuff, but we're gonna be exploring this together in this stream pretty much. And yeah, alright, so let me just share the live stream on my Discord server really quickly. We're going to be using some crates, some Rust crates, to make things very efficient. We're going to see how that would go. It would definitely be way better than your regular WGPU tutorial. Gonna try to not make this honestly a tutorial, because tutorials takes a lot of time. This is just going to be like a follow or like a code along kind of live stream, really. I'll try not to explain too much, but yeah. Hold on, let me share the stream in my Discord server really quickly. Okay, let's see. Alright, announcements. Okay, live. Alright, so I'm kind of tired of reviewing AI code. So in this video we're going to be learning a bit about PBR and Gltf spec and so on manually, hopefully, and we'll try to create something. Alright, so yeah, let's get started. Oh crap, forgot to install Rust up already. Alright, sure. Let's sudo pacman-s rustup. Okay, I'm on Arch Linux Cache OS, KDE, NVIDIA. Have an RTX 3050 just for reference, and yeah, nothing fancy. So how do you install this Rustup toolchain? I'm going to be using the nightly toolchain. You could use obviously whichever toolchain you want, just because it's probably going to be the fastest. Install nightly, and let's get started. If you guys have any questions, please let me know. And let's spin this message and let's go. Can we pop out this chat? Perfect. Alright. So obviously I'm going to be using Rust Rover, but you could use whichever IDE you want, NeoVim, or VS Code, or whichever, doesn't matter. Anyways, so yeah, I installed Rustup. Let's see if it's gonna detect it here. I gotta actually restart that. Is the stream fine? I mean, my mic is on, no dropped frames, I think. Yeah, mostly. Alright, sick. Let's see what we got. Alright, so let's get started. We're gonna create a new project. Let's make sure we have the standard library here, and we're good. So we're gonna go with the binary here. And honestly, I'm not sure what you call this. I guess let's call it Taco Gltf, fine. Right? Gltf, yeah, sure. And yeah, binary application, and let's create this. Alright, very much love Rust, so I'm very happy that I'm back into Rust. It's my favorite programming language, but as you guys know, I pretty much program in a lot of languages like C++, C, Zig, you name it, whatever. But Rust is my freaking favorite. After that, I would say probably Zig, but yeah. Anyways, so we got our hello world here. Alright, so we're gonna add a few dependencies. Cargo add tracing and tracing subscriber, I think. Subscriber, this is for basically login and stuff, and profiling kinda. And then you got obviously the WGPU, the star of the show, and when it's the window in library. And what else we got? Well, we're gonna need GLTF for the GLTF parsing and stuff. What else? Let's see. Wait a second. Let's grab this guy here. And let's see, we're gonna need a few other things. We're gonna need an offset allocator, because I'm gonna be like loading the whole GLTF scene into 1 mega buffer instead of like having multiple little inefficient allocations in the GPU. So we're gonna be using this offset allocator in Rust here, which is pretty sick. Offset dash allocator, okay, that's one of them. We could add, like, for colors, we could add palette too. That's pretty cool. Crate 2 palette. What else? There's also the image crate if you want to load images, but honestly I'll try to go with KTX2 if possible. So the KTX2 Rust crate. Let's see, I never honestly used KTX2 directly. I've just used like the image crate mostly, but we'll see how that would go, hopefully. Otherwise we could go back to the image crate pretty much. So yeah, I think parser for the KTX2 texture container format, async reading, parsing, validating, blah blah blah, you got the point. Okay, sure. So let's add KTX2. For HDR, I don't think we're gonna be doing HDR in this stream, but to some point we're gonna go with EXR, hopefully. I think, yeah, EXR. Anything else we're gonna need? Yeah, and another one that I'd like to try in this stream is WGPU, I think bindgen or something. It would basically generate for us the what is it called, you know, the bindings and stuff, which is pretty sick. And like the, yeah, this is the one, I think. Yeah, it generates type safe Rust bindings from WGSL shaders for WGPU. This obviously runs in the build step, not on runtime. And yeah, it uses Naga oil. So WGPU under the hood uses Naga to compile your WGSL to GLSL or SPIR-V or whatever. But Naga oil, on the other hand, adds for you some includes to your shaders and stuff, and some other cool stuff. Like for example, you could right now say import, and then it would basically turn it into, it would pre-process it essentially and give it to the WGPU for you essentially. And yeah, pretty much. But anyways, so yeah, but this one should be a build the dev dependency essentially, not really a runtime dependency, I believe, unless if I'm wrong, but yeah. Right, wait, what WGPU it uses though? It seems to be, I guess, using, all right, let's just add these first of all. I think we're also going to use GlamX math crate. So let me show you GlamX on the other hand. GlamX. So GlamX is basically just an extension library of Glam, which is like the usual default library, but it just adds some few things, pretty much. It's made, I think, from like the N-Algebra team, because yeah, there you go. This is the guy who made the Rapier physics engine. So basically, they were using N-Algebra, which is their own dog fooding, you know, math library for the physics engine. But then they kind of moved on to GLAM, but they still needed some few other things extra. So they created GLAM X, which is just an extension of GLAM. So we're gonna be using that one. It's pretty sick as the math library. And yeah, I believe that's probably it. So yeah. Alright, back. Okay, let's just, I guess, get started already. Let's just add these. We're not going to be using all of these today, but soon enough, once we get to it. But yeah, we'll see. Alright, so let's get started. Did I miss anything? Not really. So we're going to be obviously using the latest versions of everything. Okay, beautiful. Let's just try to run this, I think. Preparing data for name resolution, analyzing. Okay, hold on. Until it's done. Well, that's gonna take a minute, huh? Project analysis enables smart features like refactoring, find usages. Alright, let's try right now to run this. So just compile everything. Yeah, we're also gonna need ByteMuck, I believe. We may also want to use in-case for uniforms. Yeah, there's quite a lot of cool crates, to be honest. And yeah, it's pretty easy to add in Rust. But there we go. Okay, hello world. Alright, let's see what we got now. We're gonna create an event loop. Is equal to event loop. And new dot. Oh yeah, we're also gonna need anyhow. That's true. So let's add anyhow really quickly for the error handling part. Anyhow. And ByteMuck, yeah. Cargo add ByteMuck. And I believe for GlamX, we're probably gonna need the feature ByteMuck. So GlamX -- features ByteMuck. Right? Did I add that? Yes, I did. And finally, probably like in case for the uniforms, I believe. But we'll see. There's also crevice, but I'm not sure. Hold on. Crevice, Rust. I don't remember what this was about exactly. Generated provides to allow safety back into buffers for uploading. I wonder what's the difference between crevice and between in-case and crevice. Rust crates. Let's see. Yeah, so they solved the same problem, interestingly. Oh, crevice is actually made for GLSL, not Web GPU, huh? Okay, never mind. Alright, so cool. Okay, so that was it. Let's see now what we got here. So we're gonna say anyhow result. And there you go. And just gonna return okay here. And when it changes very quickly, so I'm going to show you how you could use the new API, obviously. So you basically create a struct app, then you implement the application handler for app, and let's implement some members. So there's a few things about here. There's the resumed, the window event, there's the about to wait, whoops, window resumed, and suspended, exiting memory warning, blah blah blah. You got the point. So let's add these and let's see what we got here. Okay, so we should start building our stuff in resumed, and we should destroy our surface on suspended. This is important for Android and iPhone app lifecycle, and maybe even a bit of macOS, just to save some memory and stuff, I think. But yeah, either way, basically when your app goes to the background, you gotta destroy the GPU surface and recreate it once you resume, once you're back into the foreground. But yeah, all right, so how are we gonna do this? So we're gonna have a state here, which is gonna be like an option state, I think, and we'll see about that. And let's see what we got here. Okay, so state, or no, fine, let's just do directly, I guess. I mean, yeah, let's just do it directly for now. We'll see about that. So we're gonna have like an option WGPU instance, and obviously this will derive from default, and we're gonna have like, so after instance we're gonna have oh yeah, by the way, we're gonna also need the pollster. So we're not gonna bother with the web compatibility for now, though it's definitely a possibility, but for now let's just use pollster. Cargo add pollster, and let's go. So just a little async runtime, just so you can get to run WGPU async functions. But yeah, other than that, you're gonna need device and queue. So like option WGPU device, and queue is option WGPU queue. And I believe that's all. Obviously we're gonna also need like the surface. So for the surface, we're gonna go with WGPU surface, and it needs some lifetime here, which we're just gonna go with static, because we're gonna be using arc for the window. It's not implemented for, oh, well, obviously you're gonna go ahead and say option here. Yeah, instead of option, this is, yeah, no way. Let's just do that thing that I was talking about, fine. Let's just do it. Let's just make a struct here called state, which would contain all this stuff, and obviously also this stuff here. And the surface, this is gonna be, I believe, optional, yeah. Other than that, we're good. So in here, just gonna have like state is option state, I think. Yep, cool. So essentially, if we have some state, so if let's I guess state is equal to self.state, right? Then we got our state here. Obviously, we gotta use this guy. I believe maybe mutable or something. We'll see. Do we really need mutable access? I'm not entirely sure about that. Maybe not, but anyways. Else, if we don't find any, which means here we're just initializing, here we're just resuming, kinda, basically. But yeah. Alright, so what we're gonna do. So on init, we're gonna basically create a new instance. And I believe there is a pretty cool util function for that. We could, I guess, initialize, like, sorry, instance. Could attack, we need more Zig projects too. Wei Sing, welcome to the live stream. Currently I'm not into Zig, but if I ever get the hint for making like Zig project, sure. Sure. Just like I did with Rust now. But yeah, new instance with web GPU detection. I'm not sure what's that about exactly, huh? Create a new instance of WebGPU but disabling browser WebGPU if no WebGPU support was detected. What? You should prefer this method over instance new if you want to target WebGPU. Automatically fall back to WebGL if WebGPU is not available. This is because WebGPU support has to be decided upon instance creation. Instance new being a sync function can't establish WebGPU support. Oh, what? Backends remove. Huh. Interesting. Well, I mean, fine, who cares? Let's just use it. Fine. And here we're gonna need an instance descriptor. And well, they changed that, huh? So there's a few functions right now. There's new with, so there's all these new functions apparently with display handle from NV. So there's these cool from NV functions. Let's check them out. So there's this with display handle and without display handle. I would guess we'd better use with display handle if possible. Let's see what it takes exactly. It takes a box, then WebGPU has display handle. How do you get display handle? I believe probably from event loop, but how exactly? I don't know. We'll see. Alright. Is there any expected found active event loop? Let's see if there's any hint by any chance for that. Okay, let's see. Maybe box new. Maybe we're supposed to do box new here. Let's see. Mutable cannot be shared between threads safely, huh? Cannot be shared between. That's interesting. Let's check out the documentation really quickly here and let's see what we got. So basically new without display handle. Let's see. New display. What? WGPU has display handle. Okay, that's interesting. Well, I guess maybe... Is there an example in WGPU crate? Hold on. Let's check out the examples here really quickly, because they keep on changing this crap. I'm not sure why they did that, but anyways. Let's see the hello window here. There you go, Polster, WGPU, and Winit. And they're even adding this Android native activity for some reason. I guess maybe to support Android, I would suppose. But yeah, obviously we still also need this window thing, but we'll see about that in a second, I guess. New with display handle box, new display. New with display handle. Okay, where they're actually calling that thing. They're not handling that that surface destruction, but anyways. Okay, so you just say event loop the own display handle. Okay, fine. Event loop dot own display handle. There you go. So that works. That works. Perfect. So that's your instance, but obviously this returns a future, meaning it's a async function. So, well, if we were in an async function, we would just say .await and you're done, right? Like here actually. But obviously we're not an async function, so we're gonna use Polster for this, and we're just gonna block So pollster would basically just turn this async function into a synchronous function, which we just wait for it to you know, finish up. But yeah, block on. So we're gonna block on this async function here, and we're good to go, I believe. So that's your instance. Next up, well, obviously we're also gonna need our window, and for our window we're gonna use this arc, so it could be basically shared between multiple threads and so on. In this case, we need an arc surely for sharing the ownership with the surface, so we could actually use this static. Otherwise, you gotta make it a reference and keep track of lifetimes and crap like that. But anyways, so after creating the instance, let's see how we could create the, well, obviously we need to also create the window though. So I mean, fine, let's actually create it here. Fine. So window is equal to what? To event loop dot create window, and window attributes, and default, and yeah. Now obviously this could fail, so let's just do that thing. Well, so you know what I'm gonna do actually? I'm gonna implement app, and I'm gonna say fn, not really new, but like, actually let's put it inside of state. Let's put it inside of state. Impl state fn new, and then result self. Well, obviously anyhow result. And we're just gonna grab this part here, and we're gonna put it here, and we're basically, else if there is no state, then we're gonna basically say self.state is equal to some state new, too simply, and we're just gonna unwrap, and boom, done. Alright, so obviously we're gonna need some event loop here, so let's just pass it up into this new function here, and let's pass it up here too, and you're good to go. And here we're just gonna say self.state, well, or sorry, state.resume, right? State.resume. And yeah, I believe so, like fn resume, and this also would basically return an anyhow result. Right, so how this would work exactly? What do you mean by import? Oh, well, this should take in a self, I would guess. And this could fail, so let's say .inwrap here too, and we're good to go. And yeah, so if there's already a state, we're just gonna resume that state. Otherwise, we're gonna create a new state, too simply. And when it comes to suspended, we're gonna suspend that state. So state.suspend, pretty much. .inwrap, I believe. Nah, I think maybe we don't need that. Fine. And obviously, well, self.state.suspend. So fn suspend self. Well, we're probably gonna need mutable self, but we'll see about that, I guess. Yeah, and here we're just gonna basically make sure that the surface is dropped. And for that, we're just gonna say self.surface is equal to none, too simply. And on resume, we're gonna recreate the surface, etc. And honestly, after creating the state, we're gonna resume it. Or we could do it here even afterwards, after here. Well, actually we don't have self here, so we can't really do it here. Fine, let's just do it here. Okay. State.resume. Oh wait, what the heck? No, not here. Here. Right. And well, you just gotta say self.state. Wait, what? No, let's just say, okay, fine. Let's say state is that. Let state is equal to this, and then state.resume inwrap. And there you go. Alright, so after creating the window here, what we're gonna do, we're gonna return self obviously, and let's see what we're gonna do next. So here we're gonna create a temporary surface which gonna get destroyed. So temporary surface here is equal to what? To, I believe, maybe instance create surface, right? And just pass it the window or anything basically that could, you know, that basically implements this kind of trait into surface target essentially. Because like you don't really have to use WinIt, you could use SDL or whichever other window in library. But well, anyways. So after creating the temporary surface, we're gonna, well, I guess grab an adapter, right? I believe. Request an adapter, yep. And the options, so request adapter options. Well, hold on. WGPU request adapter options. Interesting. Anyways, and actually this, since this is an async function, we're just gonna make this async fnu. And how are we gonna handle this? So obviously we're gonna just say the await and then unwrap the result, and let's see what we're gonna do here exactly. Let's add the missing fields and let's see what we got here. So I'm only gonna change this compatible surface to some temporary surface just so we could select. So I basically created this temporary surface just for the adapter compatibility stuff. Other than that, I don't think I care about the other options. Force fallback adapter, apply limits. Yeah, I don't give a crap. So just remove that stuff and let's just say .default. So basically initialize everything else to their default values. Now that we got our adapter, we could grab our device in queue. So adapter, I guess the request device, let's go. And then here, device descriptor, well obviously WGPU device descriptor. Well, let's see what we got here. Let's add the missing fields. So we could give some debug fields, I don't care. Required features, you could set these to required limits, experimental features. I wonder what kind of experimental features we have. Interesting. Link to, that's interesting, but anyways. And even some memory hints for memory allocation strategies. Okay, you could select either performance, memory usage, or manual. Performance by default. Interesting. To fewer device memory. Okay, I see. So it basically sub-allocates the memory, the backend memory. Interesting. And there's even trace. This trace is pretty interesting too. Especially if you want to debug, like let's say with an AI agent or something, that basically you could give it like a file path, I believe, if I remember, and then it would basically write all the API calls that happens to WGPU for you into the logs or into a file, I think, or whichever, and then you could basically read all the API calls. It's kind of like Vulkan API dump layer, if you know that one. But anyways, yeah, pretty much I don't really have any particular need here for anything special, so I'm just gonna go with the default stuff. And finally we're gonna wait and unwrap the results, and there we go. Now obviously I'm gonna also like store the, what is it called? Honestly, the window shouldn't really be here, shouldn't it? Good question. Nah, let's just keep it, I think, there. Fine, who cares? Okay, next thing I'm gonna add is the adapter, obviously. So instance adapter and device adapter, WGPU adapter, and honestly, before even the adapter, actually we could put the surface the last thing. Fine. Okay, it doesn't really matter. It's just like, you know, yeah. Anyways, what we got here? Okay, so this should be okay self, and then we could add all the missing fields here. Oh yeah, I forgot one little thing here, which is the window should be put into an arc, so we could share ownership. Other than that, we're pretty much good to go, and we will have no surface at first. So this temporary server just get destroyed. So we keep things very simple. I mean, we could have just like, you know, kept around the temporary surface as the actual surface that we're gonna use, but just to keep things isolated, you know, the resume is the only function that would actually create the real surface, kinda. But yeah. So the window is actually moved here. Well, we could just clone this. So here we clone it, so the surface gets basically like ownership too. So we kind of share the ownership. One clone of the arc, it belongs to the surface, and one clone we just keep it around for us. And yeah, that's basically it pretty much. That's for the initialization there. Cool. Next up here in the resume, what we're gonna do is self.surface is equal to, well, pretty much same thing here. Instance create surface window clone, I believe. And I think we're gonna need mutable access though here. And self window.clone. Convert to option. Hello, Barryissa. Welcome to live stream. Welcome back. Okay, found. No way. What's up? Okay, I didn't program in Rust for a while now, and we're back. We're back. Expected option. Yeah, let's just go with some, I guess. Yeah, fine. Back to raw fun. Yep. Let's go. What's going on here? Oh yeah, anyhow result, fine. Well, do we yeah, we need it, right? Let's just say okay. And we're good to go. So that's the resume and that's the suspend. Kind of set to be late to a no LLM stream. Yeah, no LLM, yeah. We're gonna try to not use any LLM. Except for, at least for today's stream, except for, you know, just a bit of Gemini from time to time, just in the web chat. No AI agent though, at least for this stream, but we'll see. Okay, so what's going on here? No method named in wrap. State new. Oh yeah, we gotta make sure to say await. But obviously we don't have any await here. We gotta say block on. So we're gonna say poster block on. Well, let's go. And boom. And what we got next here? Let's make the state mutable so we could resume it. And I think we're good to go. And yeah. And obviously we do need to handle the event here. Match on the event, and basically if we got like a quit event, I believe, yeah, sorry, close requested, then we're gonna say event loop.exit. There you go. And obviously for anything else, we're not gonna do anything for now. And in the about to wait, here where we're gonna render some stuff, essentially. Okay. And set.state.suspend. Yeah, I see. So, well, I mean, if let some state is equal to self.state, then state.suspend. I believe make state mutable. Well, actually, let's take mutable reference here and we're good to go. Alrighty. And here we got like, well, same thing pretty much. If let some state, then we're gonna try to render that state. And obviously I don't have a render function just yet, so let's add that one. If then render. I'm not sure if I'm gonna need mutable access though, but we'll see. And obviously this probably could fail, so we're gonna say like anyhow result. Let's see. And yeah, I guess that's good. So I gotta make sure to configure the surface first of all though. So on the resume here, after we create our surface, let's see what we gotta have to do here. Yeah, self in wrap.configure. Okay, well, I see. So let's grab this surface maybe. Like this, and then we can say surface configure, and here the device. So it's basically going to be like self.device, and here the config. Surface configuration. Like, do you fill this by myself or what? Let's see. Oh yeah, I fill it myself. Okay, so self.surface format, blah blah blah. Alright, let's just try it ourselves and then we could see what's up. So the usage. Well, I would guess render attachment because we're gonna render to this guy. The format, we could storage. The color space, I think color space is probably fine by default. Let's see. Color space, right? Okay, so I have no clue what these color spaces are about. Let's see. Let the backend choose the color space, reducing WGPU historical behavior. Format is texture format, RGB is 16 float, so supports separate format, otherwise it's RGB. Okay, so that's basically the default, so we could just keep it as it is, fine. So we could just say .default for anything else. And for the width and height, we could go with the where they grab the width and height here, self.size.width. Size. Let size is equal to that. Okay, cool. So we're just gonna grab it from the window essentially. And for that, we're gonna go with well, I mean, we could probably just go maybe with width and height like this, and then possibly say let width comma height is equal to self.window.inner size. Is that right? Wait a second. Did I actually make the save actions here? Yes, I did. So there's something wrong with this guy. Maybe I could say intro, possibly. Right? Yeah. Oh, I just need a semicolon here, that's why. So do I still need the into here? Yes, I do. Okay, fine. And here the surface format. Let's check it out. Surface format. Well, we probably gotta grab it from, I think, the surface capabilities, right? Yep. Okay, fine. Surface capabilities is equal to temporary surface dot capabilities, and then the adapter. And yeah, so surface capabilities dot, and we have a few things around here, but here we only require formats. Well, what they do here, they just grab the first format. Fine, that's enough, that's good enough. But yeah, okay. Well, obviously gonna say let surface format is equal to that. And then here we're just gonna have surface format is WGPU format. And yeah, add the missing fields. Boom. Anything else? Honestly, I'd rather put this guy here. Just nitpicking, nothing fancy. It's not important, but yeah. So that's all. Right. Cool. Now the present mode. The present mode, what they did here. Present mode, they did auto vsync. That's good. I wonder if it's the default though. Honestly, mailbox is way better, but auto works fine too because they have fallbacks, which is nice. And is that a default by any chance? No, the default is FIFO apparently, which is interesting. But auto vsync would either choose FIFO relaxed or FIFO if FIFO relaxed doesn't exist. Yeah, the mailbox is honestly pretty much the best, but anyways, whatever. So yeah, that's fine. Next up is desired maximum frame latency. This is basically a trade-off between, input latency and frame rate. So the bigger this is, the more room for the GPU to prepare more frames, or maybe actually more room for the CPU to prepare more frames while the GPU is still working on. So you could get more frame rate, but at the cost of bigger latency, because you're going to be rendering some frame that you prepared like 70,000 years ago, right? The more you increase this value, essentially. But yeah, but like the default is just 2, which is fine. Yeah. I obviously over-exaggerated there. So 2 is the usual value. If you're working on like some sort of I don't know, some FPS game, which you need the smallest latency, you probably want maybe, I guess, 1. Yeah. I don't think you could say 0 here. If you want more frame rate at the cost of a bit of added latency, then go with 3 or even more if you'd like, but yeah. Anyways, that's enough for that one. Next up, the view formats here, which we basically have a vector. Request compatibility with sRGB format texture view we're going to create later. Honestly, I didn't understand very well this is, but I remember I've researched a bit about it with AI, and it kind of told me about the fact that I believe maybe in Android there was like some weird thing where like it doesn't support sRGB, like the Surface doesn't support sRGB, but you could add some sRGB view or some crap like that. I don't exactly understand what the heck, but just do it this way. But if you guys know what's up with that, then let me know if you guys have some good explanation for that part. Anyways, let's just go with this. Okay, so we're gonna go with surface format and wait, what? Why don't you have the add sRGB suffix thing? That's strange. What? Am I missing something? Whoops. I feel like I may be missing something there. Let's see. So first of all, this guy. What? Really? Something fishy going on here. Oh, okay, I see what happened there, I guess. Well, I am using WGP format. What the hell? If you import format, refer to it directly. Oh man, it's always too late here to keep up. Yeah, I pretty much live stream late at like in the middle of the night, at least for me. If you import format, refer to it directly. This is too range. Watch. Oh, sorry, texture format, I believe. Yeah, that's probably was the issue, I would guess. Oh, there's no default here. Fine, that's interesting. Okay, so what you require is color space. Fine, let's just, I mean, we could just do default, honestly, but at this point, instead of doing that, let's just go ahead and do it. Fine. Color space auto. Fine. And yeah, that's basically how you do it, I think. And what's up with the alpha mode here? Alpha mode, auto too. This is basically for transparency, I would guess. Well, let's just go with auto. What it does. Choose either opaque or inherit automatically depending on the alpha mode that the current surface can support. Okay, cool. And yeah, I believe that's pretty much it. And then finally you configure the surface. Yeah. Wait, what? Oh, I see. Gotcha. Configure surface. Alright, that's good. That's great. Next up, we also got the resizing. So when a resize happens, what we do. So window event, resized. And, well, we could just do this, I guess. And then we're gonna basically say, well, self.state. Well, basically if let's some state is equal to self.state, then self.state.resize. Sorry, state.resize, yeah. Though I believe maybe the resize already gives me the, yeah, it already does. Cool. So we could grab that, fine, whichever. And then we could pass it up. Although we could just grab it from the window, to be honest. But fine, who cares? Okay. So let's add a new function here called resize. And honestly, I'm gonna put it on this guy. So how are we gonna do this? Let's just grab it from here. And let's say fn resize. I'm not sure if we're gonna need mutable self here. We'll see about that, I guess. And so just say surface.configure, self.surface.configure. Oh, what? Well, dot in wrap. I mean, you could say if let some surface, but honestly, I don't think. I mean, fine, just to be safe, fine, who cares? Let's say surface. And let's say if let some surface is equal to cell.surface. That's what's nice about Rust, is that it kind of forces you to kind of think through if what happens when the surface could possibly be in a non-state, what you would do about it. Would you just enwrap and just assert that it's always there, or would you check it out, or what exactly? Anyways, and here the width and height. And for the width and height, you're gonna go width u32 and height u32. Right, and then here we could just say self.resize width comma height, and let's go. Well, obviously, I guess just a reference. Mandatory error handling, hell yeah, yep. I mean, at least it's way better than C and C++, where like you just gotta figure out what errors have going on, or like what thread safety, and if there's no documentation, you gotta check the source code yourself. If there's no source code, then well, you're in trouble. Yeah. Like for example, printf. Printf actually returns like an integer telling you like if there is an error or not. But nobody really cares about the error of printf. But anyways. Okay, so I believe that should work. Where is that? See, cannot borrow mutable local as mutable. Does the resume really need mutable access? Like, yeah, it does. Gotcha. Fine, let's do mutable there, and yeah, and we're good to go now. But like the resize, perhaps checking the exact source code doesn't always help you. Yeah, so another thing that I kind of hate about C++ honestly is when you debug. At least it's not the case in C. At least when you debug in C, like everything is in line. But in C++, when you debug, you kind of gotta go through multiple initializer lists and like the STL written by some, I don't know, non-human people. But yeah. Okay. So where are we? So we make sure to resize. And what else we got? Where do we resize again? Yeah, and we're resizing obviously in the resized event. But what's going on here? I guess you're gonna need, or does it need like mutable access again, or what? No, wait. Inner size dot width and inner size dot height. Cool, and I believe we could just grab only the reference, fine. Okay, and finally the render function. So I believe this did change a bit from the latest API I've used. So let's find out what's going on here. Okay. Surface dot, let's see what we got. Is it in surface or is it somewhere else? So like you acquire, I guess, or like device acquire, or I could never remember. Let's see. Actually, they're doing it in redraw requested, interestingly. And then they're requesting the redraw again. I see. Alright, fine, let's do it. But okay, what they're doing in render here. Cell.surface. Oh, get current texture. But now they actually added these weird errors right here. Yeah, basically from the Vulkan swap chain bullcrap and stuff. But anyways, so get current texture, right? Well, obviously we gotta make sure that we have a surface first of all. That's why. And yeah, now what they're doing here is that they're matching on that. And if it's success, then they're just returning the texture. If it's occluded or timeout, then they just return. Okay, so basically kind of like maybe if the window is minimized or whichever, then they just skip this frame. Otherwise, if it's suboptimal, then they drop that texture and then they try to reconfigure the surface. And if it's updated, they try to reconfigure the surface again. I see. And validation, if there's a validation error, they just say no error scope registered, so validation errors will panic. And if it's lost, then they just create a new surface and configure the surface again. Interesting. Well, for now, you know what? Who cares? Let's just see. And just do this, I believe. Can we? Oh, cannot be applied. Okay, so smart. smart. Fine. We could do this. Success. Wait, what? Otherwise, for now, let's just say and implement it. Okay, and what's next? Expected anyhow. So now that we got the texture, next step, well, this is, they call this surface texture, fine. Next is the texture view. So just, or you know what, fine, let's just copy this whole thing right here, really, call it a day. Fine, whichever. And let's just use self-select match surface gate current texture and timeout. We just return, I guess, okay. And here configure surface. Well. Thinking what I'm gonna do about this one. I guess we could just just say resize, I guess, fine. And we're just gonna grab the width and height. I mean, we're gonna need probably the width and height here anyways in the frame, so I guess fine, let's just put it here anyway. And just to be good citizens, let's call this window width. And let's call this window height. And yeah, alright, and let's just copy this here. And what's going on here? Make self-mutable. Sure. And let's put that guy here. And here we're gonna see some. Create service, self-window clone, and let's just do this. And yeah, and here finally we're just gonna say okay, I believe. Well, we're gonna do okay here too. Do I actually need return though? I don't think I need return, or do I? I think I do actually. Fine, whichever. And here, unreachable, no error scope registered, so validation errors will panic. I don't know. Fine. And I guess that's basically it for that part. Next up we got texture, and we create a view with might not be gamma correct. Fine. We're gonna call it texture view, okay. I mean, surface view is equal to surface texture, well, what? Create view, texture view descriptor, add the missing fields, and let's see what we got here. I think we could just say default, right? Yep, but the format though, on the other hand, you gotta set it. Fine. So the format is basically, I guess, sum, right? Yep. So some self-surface format, add sRGB suffix, and for the other stuff we're just gonna set it to default apparently. Okay, fine, whichever. Anything else? Yeah, I believe that's it for that part. And finally we just create a command encoder. We begin a render pass into that texture view. We clear it obviously with a green WGPU color. We store that and we drop the render pass, and then we queue submit, and then we present, notify, and present. Okay, let's create a command encoder. What they called it here? They called it encoder. Okay. So self.device.create command encoder, I guess. And here we're gonna need the command encoder descriptor. I would guess the default is probably enough. Yes. And next, I mean, if everything goes well, just gonna return okay. Okay. And here we're gonna start a render pass. So you could either like manually drop it at the end, or just, you know, create this little block here. Begin render pass or compute pass. In our case, it's begin render pass. And then we're gonna create this WGPU render pass descriptor. Well, hold on. And let's add the missing fields here. Okay, so I guess we don't care about, do we have the default implementation by any chance here, or do we just gotta do it? I mean, maybe. So I guess we could probably just remove all this crap and only keep the color attachments. And the color attachments here is basically options. So some render pass, well, a render pass color attachment, add the missing fields, and obviously here we're gonna go with the surface view. Depth slice none, the resolve target none. I wonder if there is a default here too, because it's not always the case. Yep, in this case it's not the case, so fine, let's keep it. Now for the OPs here, what are we gonna do? Let's see. I wonder why they put it into a struct, because before it was just, you know, another field kinda. But we could see about that. Wait. So for the load OP, we're gonna clear, obviously. Well, WGPU load OP clear, and then you give it some value here, which is obviously WGPU color, and then you could just say green, red, whatever. Let's go with red. And for the store, well, we're just gonna store it, obviously. But is storage the default? I don't know, but honestly, since it's one thing, let's just do it anyways. Who cares? And yeah, so that's your render pass. Currently, we're not going to be using it, so fine. Next step, finally, we're going to actually submit that to command encoder by finishing it first, which would basically give us back a command buffer. Then we're going to submit it to GPU, present notify, and then present the surface texture. Cool. So obviously after this kind of block where the render pass would end, kinda, or you just drop it essentially, where it would get dropped, we're gonna say self.q.submit. And then here you could honestly just say iter once, since we only have one encoder here. And then we could say encoder finish. Either iter once, or you could just use this kind of thing, you know, just a little array with one element essentially. And yeah, next step, you just pre-present notify. Okay, and finally we're gonna present the window, and we're gonna pass in here the surface texture. Surface texture, wait, surface texture. There you go. Okay, cool. And yeah, I believe that's pretty much it, probably. Hold on a second. I'm just gonna grab some water. Okay, back. And now let's see, did we get this or no? Obviously we have a little error here. If may be missing an else clause. Really? Oh, I see what's up. Let's just grab this okay and put it here instead, outside of that if. And see, let's just do this. And wait, what? Oh, we didn't run the app yet, so let's make sure to do that. Run the app, and here we're gonna say mutable app default, and we're just gonna unwrap the results, and let's go. And boom, you got your red window. Everything looking great. Wait, what the heck? It's a bit slow. That shouldn't really happen. Am I pre-presenting notify, by the way? Yes, I am. Last time I tried WGPU, is actually not that slow for some reason. Okay. Adapter. Apparently I'm not using adapter currently, but that's fine. Yeah, pretty much. I'm also not using the window ID, but I could if I want to. Like, should we handle multiple windows? Meh, no. No. And so, since that's the case, we're just gonna ignore the window ID. And okay, what I wanted to do, oh yeah, let's just go with one thing here actually. If I draw nothing gets like 2.5k FPS. I wonder how can I get the FPS. Should I just like do some Like, I could use tracing though. I think I could use tracing, maybe instrument or something, and then it would just do the job for me, I think. But anyways, yeah, instead of about to wait, I think the problem here is probably just the fact that I need to use window event redraw requested. Yeah, that's probably why, actually. And then you gotta make sure to wait. And what they do afterwards, like redraw requested, I believe they request the redraw again or something. Okay, so apparently they request the redraw multiple times here for some reason. Wait, I can't type. Oh my god. Request redraw. So they're doing it right after a redraw request. What? What? Like, wouldn't that cause it to... Oh, never mind. So basically we want to keep on redrawing every frame. So every time we get a redraw request, we just render and we try to request another redraw. So that makes sense. So state the window dot request redraw. Right, I think so. And finally, the other place where we do that is after the resume, apparently. After the resume. Window.request redraw. I mean, we could do it here, fine. Request redraw. Well, how are we gonna do that? Well, we gotta do it actually in here. Yeah, fine. Let's just do it in the resume function. So you're gonna say self.window.request redraw. Okay, let's try this out. Alright, that's way smoother. Look at that, man. Look at that. Alright, lovely. Okay, and that's how you make a clear window in WGPU with proper handling for Android 2, which the example didn't include for whichever reason. Not sure why, but they didn't. But anyways, so you know what I'm gonna do right now is let's see. Should we split this up already or no? No, I think I'm just gonna leave it up here. Put up mango. Okay, so let's see what's up going on here. Do we have get ignored? Yes, we do. But we're gonna add a few things. We're gonna add the idea, and we're gonna say init. Well, not really init. Wait a second. I'm gonna call this clear screen too simply, and commit, and let's go. And boom. Alright, so we're gonna move to the next thing, which is I guess a triangle. A triangle. And let's look for another example. You know, for making this very easy for people and even for myself, I'm gonna keep the whole code in one file instead of splitting everything up, which is really confusing. So yeah, okay, and let's go back to standalone here. Let's try to find some hello triangle thing. Where's the triangle? Okay, there you go. Hello triangle. Well, where's that? Oh, there you go. The holy triangle. Okay, there you go. Just gonna save that up. And we're just gonna make, I guess, maybe an assets folder. Or no? I mean, I'd love to actually, like, right now set up this if it's if it would be able to. Let's see. The one thing that I've noticed, okay, crap, 4 months ago for some reason, which is interesting, I'm not sure why. Well, that's a red flag. Cargo trouble. Yeah, they're using WGP 29, so that could give us a lot of trouble. So no. That would have saved us a lot of work with the bind groups and, you know, vertex formats and crap. But unfortunately, they don't support the latest version. Okay, how about Naga Oil? I've never tried this one, which is obviously from Bevy Engine, but I don't think it depends on Bevy. Yeah, it doesn't. But WGPU version 30, which is right, the one that we're using here. Yes. Which is cool. Alright, let's see how this works. Have it changed significantly in the latest version? And probably is useful externally. Naga organized? I've never used Naga Oil, but it's interesting. Probably is useful externally. And I don't know what's up. I'm gonna drink some water again. Okay, back. Let's see. The compose module allows construction shaders from modules, which are themselves shaders. Okay, so how do you use that exactly? Is there an example here? I don't see an example here. How about here? Gltf PBR. What? Don't tell me we're gonna find the PBR shaders that we're gonna steal here. Well, the problem is I don't understand any of this bullcrap to steal it. What the heck is going on here? Make shader more. Oh, wait. So this is like multiple examples here. Sorry, multiple tests. So initialize the composer. Load composable. What the heck? Where is that coming from? Is that like a function there, or? Oh, it's this. I see. And composer.add composable module. Have you seen the Open PBR initiative? No. Are there like standardizing the Open PBR stuff? Like the PBR stuff? Yeah, I'm so behind on PBR. I've never actually implemented the PBR renderer before. This is going to be the first time. So, specification reference implementation for the Open PBR surface shading model. Material X? What the heck is this Material X? Bro, how much standards there? It's an open standard for representing rich material and look development content in computer graphics. It'll get expectable and interoperable results across software. Yeah, but what is this Material X? Okay, hold on. What is Open PBR initiative? And it's Material X. Let's see. Okay, back. Let's see what we got here. Open PBR, Open Physically Based Rendering, is an open source standard for describing digital materials to different like moving asset. I thought PBR was already a standardized thing, but apparently no. Okay. Is there Rust crates forge? Creating a PBR render in Rust and WGPU. Blender recently added thin wall translucency to follow the spec, and it's kinda awesome. That's interesting. Because OpenPBR is natively coded into Okay, so I just gotta read the spec and basically implement it. Okay, implements its Uber shader logic directly inside your WGSL shaders. You can now get proper glass and leaves from a single plane. User requires solidified geometry. Interesting, because OpenPBR is an open mathematical language, mathematical specification. You can code the layers yourself. You will map your WGP uniform buffers. Core structs, create uniform structs in WGSL. Continue. So if I subtract the topic, but it'd be kind of good to know, at least keep in mind. Yeah, I'll definitely keep in mind. That's actually pretty good, because, well, we're going to be implementing this hopefully eventually. And so I'm always looking for standards or like Rust crates to use or stuff. So basically to adopt instead of like reinventing the wheel. So that's pretty good that you told me about this. Open standards, yeah. Right helper functions for the advanced layers. Yeah, it's pretty good to know, but we're still far from this. Yeah. Anyways, I think let's now go back. I'll definitely have a look into it later on, though. But yeah, alright, so let's go back into our little triangle here and let's see. So we're just gonna snatch the shader. Alright, so okay, we were into Naga oil, right? Will we use Naga oil or not? That's a good question. So we basically give it the source, okay, the file path, and some default stuff, and then it either gives you the module and or an error. I see. And here what they're doing, so they're initializing the composer, which is basically this. Okay, so wait, so you're supposed to like load every one of these manually? Interesting. Why not just loop through all the folder? But anyway, make Naga module. You give it the source, the file path, and then the shader definitions, and then it gives you back the actual shader module. And then you could create a validator and validate that module, and then Naga back, which I would guess it's the backend, WGSL write string, module info Naga back, WGSL write flags, explicit types. Yeah, I don't think that's going to be useful for us for now, at least. But I'll definitely keep in mind this one too, Naga oil. It's good to basically modularize your shaders, right? So you could use multiple shader files with includes and so on. You can only do that using Naga oil. You can't do that just using WGPU alone. But yeah, we could come back to this later on, I think. Fine. For now, let's just take the shader, put it straight into the source directory. Fine. There you go. What the heck? Please define the associations. Fine. Well, what can I say, bro? I guess just go with text for now, I guess. Yeah, fine. And do you want yes added, please? And there's even a WGSL support plugin. Sure. And let's go. Okay, so we basically just have like the built-in vertex index. Okay, so we don't need any buffers here. And it returns the built-in position. And here they're just kind of like calculating the They mention it in the feature flags. What is it? And like here, just calculate some x and the y from the vertex index. So basically you don't need here, like if you want a triangle, you don't really need a vertex buffer and an index buffer. You could just calculate it in the fly using this little formula here, just from the vertex index. And then you return this too simply, and boom. And for the fragment here, we're just returning red apparently. And yeah, nothing fancy there. Alright, so let's go back and see what we could do here. So where I'm gonna do this, I believe we're gonna do this in the new function. And let's see. Well, how do you do this? Hold on, let me check out the example. So let's just remove nega all from here for now. And let's remove this one too. And let's go back to the hello triangle example, mod.rs. And what's going on here? Oh, they're storing the surface configuration. Okay, so obviously we're going to create the render pipeline. And they even have an app state initialized, loading, and running. Okay. And the proxy, event load proxy. What the heck is that? Interesting. Triangle action initialized. I guess that maybe that's some sort of winit custom event or something. We'll see. And the window they're putting outside of the state, which is interesting. Okay, so there's some interesting stuff here. So if the app is running, cool, give me the WGP state, otherwise just return. Then we configure the surface with the new size, and they do .max1. Interesting. On Mac OS, the window needs to be redrawn manually after resizing. Interesting. Okay, so like this hello triangle example seems much more richer, I think. Loading. So if not matches, cell state initialized. Loading. Default attributes. Okay, so they basically also have WASM stuff in here. Cool. And they're spawning an async task. New with display handle from NV, box new, what we did. More like greetings, fellow triangle. Okay, let's see what we got here. Create a logical device and command Q. And here, since they want to support, you know, the web, they're adding this required limits. Okay. Okay, so this is how you do it. You create your shader module. Though I believe there was like a macro that was way easier, I believe. Even. Let me see. Yeah, there you go. There is an include WGSL here, which just gives you the shader module descriptor though. So you still have to say self.device or like no device.create module. There you go. And then here you could say include WGSL. And I guess here you probably give it the path, I would guess. And boom. Next up, you create a pipeline layout which is currently empty because we don't have any buffers or whichever. So let's create that. Create pipeline layout. And here we got the pipeline layout. Well, actually, hold on. Pipeline layout descriptor, and I think we could just go with the default for now. Next, we got the swap chain keep. What? Oh, yeah, I see. And then they have create render pipeline. Okay, let's see what we got there. Render pipeline is equal to device dot create render pipeline. So WGPU render pipeline descriptor, and let's see what we got here. So label none, layout, I would guess this pipeline layout. No, well I think some, yeah, okay, some. So some, I'm not sure why you could say no, none though. Why? Hold on, is there? Oh, wait a second. If layout is none, then the pipeline has a default layout created and used instead. The default layout is deduced from the shader modules. Interesting. Yeah, I mean, for now, let's just keep it the way it is, but that's interesting. And here the vertex state. The vertex state. Okay, that's where you put the vertex shader. Then you got a fragment where you put the fragment shader stuff. And the primitive, the depth stencil. Okay, is there like a default thing here? Is there a default implementation by any chance? Nope, there's not. Okay, cool. So let's just say WGP vertex state here, and let's see what we got. Add the missing fields, please. And here the module is, well, shader, I think. Yeah, for both of them, we just changed the entry point too simply. And here, I mean, what happens if you say none though? I don't know. Anyways, let's just say some. VS main. And the compile options default is fine. The buffers, yeah, that's that. Next up, we also got the fragment, which we say WGPU fragment state. And here we're gonna say, well, how do you, wait. Oh, this should be some. Let's add the missing fields now. And the same module, but different entry point. So I guess FS main, right? Yep. And targets. Well, the target here, you give it, this is a bit similar to Vulkan dynamic rendering, but yeah, some swap chain format. In fact, even that, instead of calling it surface format, which is like the actual name of this web GPU API, they call it swap chain, which is coming from Vulkan. I would say this example is probably made by a Vulkan developer, but I don't know. Anyways, let's say apparently the into for some reason. Why? Color target, oh wait, color target state. Which includes the format, a blend, and the right mask. And then apparently you could just say into. Okay. Next up, the other things, we're just going to keep them as default pretty much, and we're good to go. And there you go, that's your render pipeline. Good to go. Okay, fine. Alright, so how are we gonna do this? We're gonna store, I guess, both. But to be honest with you, I think we could probably just get away without the pipeline layout. Maybe. Let's just try it out. And let's just say none here. And yeah, and let's just store the render pipeline. So WGPU render pipeline, and let's add that guy there. add the missing fields. And here, where are we gonna do that? In the render function, in the render pass, right? Whoops, render pass. Vulkan. Well, that's German, I guess, but I can't. Okay, let's see. Nah, not that. I guess self.device then, isn't it? Yeah, I think so. Bind. No? How do you bind the render pass? I forgot already. Vulkan, but I can't. Wait. Where is that? Oh, okay. Set pipeline. Alright. Render pass. Set pipeline. Then you just say self.render pipeline. Then you just give it a reference apparently. And we gotta make sure that that's mutable. Is there anything else? Yeah, and finally we gotta draw. Whoops, render pass dot draw. And here the vertices, which is arranged, so we're gonna draw 3 vertices and 1 instance, and that should give us a triangle. What? Well, I see what's going on here, because like our window is also red. That's a lot of red right there. So what we're gonna do is, instead of red here, we're gonna change things up a bit. Let's go with black. Okay. And let's go. And we got our triangle. Sick. Lovely. And the resizing works out just fine, which is sick. Cool. Okay, what we're gonna do next now is... Good question. Yeah, there's a lot of extra crap that we have to handle. For example, this occluded event. But that should be fine. But yeah, apparently so you don't really need to actually give it a pipeline layout. If I understand correctly, it probably just makes it for you from the actual shader, which is quite lovely. Anyways, I think what we're gonna do next now is, well, what are we gonna do next? Should we add some buffers? I think, yeah, let's add some buffers, or at least let's see maybe the examples that we got here. There's a cube example, which is lovely. Yeah, we could probably go with that next. Yeah, sure. Let's go with cube. There's even like multiple windows example, I think. Yep. Sick. Let's go with cube. And so again, we're just gonna steal this example. And we're just gonna read the code. Okay. So we got like the vertex main, location 0, position, and texture coordinates, location 1. Wait, by the way, before that actually, let's first of all, I believe, make sure that we commit this stuff. So commit, and let's go. Now let's, whoops. Now just do this, and let's see what we got. Okay, so we got the vertex main, got position and text coord, so basically 2 vertex attributes there, vic4 and vic2. gives us obviously the vertex output, which is basically the text chord and the position to the fragment shader. Right. And then here we even got like some group 0 binding 0 transform, match 4x4. And here we just do result text chord, so we just like pass in the text chord to the fragment shader and changed, but the position we do transform times position. Okay. Next up we got the fragment shader here, which takes in binding 1, R color. Okay, so it's a texture 2D of type U32. And obviously it takes the vertex results, and it returns obviously location 0vec4 for the color and so on. And then here we load the texture, add the texture coordinate times 256 for some reason. That's interesting. And then f32 text dot x slash 250. Oh, this is U32. So what it's doing here, yeah, I guess it's just scaling it up. Here on the other hand, it's just like making it the range 0 to 1 instead of 0 to 255, I guess. Not sure what the hell they're doing here, but okay. 1 minus v times 5. I mean, here they're inverting, and here too. And then they're basically scaling it up by 5 for whatever reason. Here on the other hand, okay, so here by 5, here by 15, here by 50. And here we got like an FS wire. Okay, so 2 fragments. One for, I guess, wireframe or something. Okay. Yeah, it's 0.5 here in the alpha. Okay, something strange going on there. Let's ask the AI what's up in the fragment shader. Oh, they're not using texture sample. Okay, so they're not using a sampler, they're just using the raw texture load, okay? Yes, but like why? I understood that. A high contrast stylized color. Okay, so it's just a gradient. Okay. Alright, I'm not sure. Wait. That was unexpected. I guess they're gonna be like using the compute shader to like draw this thing and then slap it into the cube. Yeah, that's definitely what they're gonna do there, I think. Oh. Well. I mean, if we really want to simplify, we could just remove that stuff and just go simple. But let's see what's going on here first of all. So we got like a vertex with a pause, a text chord. Okay. And we create some vertices for a cube. Okay. Then we create some texels. Oh, actually, I think they're not using the compute shader. They're just generating that pattern in software, I think. Get a high five for recognizing this. I don't. Okay, well count. And then here we got like a vertex buffer, index count, bind group, uniform buffer, pipeline wire. And then here we're generation matrix. For the camera, look at RH. And they're adding like an optional feature, polygon mode line and initializing. Size of vertex, create the vertices, create the buffer init, cast slice, vertex data. And same thing with the indices, and then they're creating a pipeline layout. So the first binding is the uniform buffer for the matrix essentially, and the second is for the fragment, which is like the UN texture, 2 dimensions. I mean, here they're actually doing it manually, but I wonder if I keep that without a pipeline layout, would it work still? Or would it not? Create texture, copy the ST, and then, yeah, they're just copying in the texels that they generated, like using that software function. And create other resources. So we generate a matrix with the size, and then we create a buffer init uniform, copy the ST, then we create a bind group with the uniform buffer as the entire binding, and the texture view that we've created here, and then we create a shader module, and then some vertex buffers. You give it the array stride, the step mode, the attributes. Okay. You create a render pipeline. Alright, interesting. And they're adding that transparency blending, okay? Counterclockwise, and they're adding some call mode, some backface calling. And actually this one is for wireframe, I think. They have line there. Yeah, pipeline wire. Alright, and they're writing the buffer. So they're like updating the uniform buffer. Okay. And they're setting the pipeline, setting the bind group, setting the index buffer, the vertex buffer, and they're drawing all the indices. I see. Okay, so what are we gonna do about that? Now that we know what's going on, I think for now, I'm just gonna remove this part and just remove this part. Wait, actually, maybe let's keep that one possibly. Group 0 binding 1. Yeah, I mean, for now we could just comment it out, but we could use it later on. But for now, let's just return a regular white color or whichever. Right. For the transform, I mean, maybe even that, let's just remove it for now, I think. Right. Yeah, for now we could comment that out too. And so we just got the text chord and the position. Fine. And here, I'm just gonna comment this out. I'm just gonna say position for now. And yeah, next up, what we're gonna do, we're gonna copy that create vertices here. Do you have any following LLM-less streams in plan? I mean, I don't know. It really depends on the day. But for now, we're not going to be using any LLM. Almost 3 AM here. I'll have to go. Love to follow up. Yeah, though, that was nice that you came up until now. But like, this stream would get saved, so you could watch it at any time, pretty much. But maybe, hopefully, tomorrow it's stream again. Maybe. But we'll see. Other than that, we're good. Position, text chord. Okay, let's make sure to import these. And this. These basically come from ByteMuck, too simply. And here we got 2 attributes, the position and the text coordinate, or texture coordinate. Currently, we're not going to be using the texture coordinate. Thank you, Barisa. See you later. Okay, and here we got the create vertices function, which we're going to return like a vector of vertices and a vector of indices, which is for now U16. So we're probably going to bump it up to U32 later on, maybe, especially when we get start to load some Gltf files. But for now we're good, I think. So what we're going to do next is we're going to create some buffers out of them. Okay, so we're going to have like a vertex buffer. Well, actually buffer, sorry. Buffer, and then we're going to have like an index buffer too. And let's just do them even before the render pipeline, I think. Or fine, maybe let's try to keep them fine, whichever. Okay, and next up what we're gonna do is let's try to create some buffers. So the vertex buffer is basically device.buffer init, and here the buffer init descriptor. Well, actually we're gonna do it this way. Missing fields, add the missing fields, label none, and the usage WGPU buffer usages, and we're gonna use it for vertex, I think. And the contents would be, well, let's call that function, which is gonna give us the vertices and indices. Here just gonna grab the vertices. Expected UH. How do they do that? Oh, bytemark. Okay. So we use bytemark to cast that vertices into bytes. So bytemark cast slice. There you go. And we do a similar thing to the index buffer pretty much. And you could name this whichever you want. For example, vertex buffer. This is just for debugging. Nothing fancy. Next step. You got the index buffer. So you could call this the index buffer. And the buffer usage could be index. Next up, yeah, that's basically that. Now what we're gonna do next is, so I think this is probably fine, right? Well, we gotta add the vertex buffer stuff here, actually. The format of any vertex buffer used with this pipeline via render pass set vertex buffer. Okay. Sure. So this requires option vertex buffer layout. Well, wait, control dot or no, add the missing fields. And let's see what we got here. So obviously the step mode, it's not gonna be per instance, it's gonna be per vertex, because this is a vertex attribute, not an instance attribute. So we're gonna go with WGPU step mode vertex. And the array stride, I believe this is probably meant to be the stride in bytes between elements of this buffer between vertices. This must be a multiple of vertex alignments. So I mean, I would guess the CD size of, or like, let's see, vertex size. Wait, is it? Yeah. Vertex, where is the vertex size? Sorry, vertex size. Size of, yeah, size of vertex. But why? Really? So, okay, not STD, just size of. And then you give it the struct. So that's your stride. Expected. Okay, so you gotta make sure to, I guess, say the into or something. Yeah, sure. Well, that doesn't work actually. So you could just gotta say as WGPU buffer address, or is that the case? Yep. Okay, cool. And for the attributes right now, I believe there was like some sort of macro for that part. They're not using it here though. But what the WGPU vertex attribute and the format. So the first format is basically position vec4 f32. So here you're just gonna see WGPU vertex format, float 32 x 4. So that's the first attribute. Offset 0, shader location 0. The next attribute is gonna be vic2 f32. So vic2 f32, and the offset is gonna be, is there like an offset off thing or something? Nah, they just did it like that. Interesting, huh? Okay, so there is a few macros here. One in stdmem and one in bytemock, and and text chord, right? Is that the case here? Right, and then you just say like as the WGPU buffer address. And there you go. And the shader location. Though I do believe there was like some sort of there you go, vertex attr array. Don't remember though how it's being used. Here you go. This is how you use it. So you just do something like this. Right, so in our case it's gonna be 0, 1, and the first one would be like 32, 4, and the second one would be 32, 2. Right, is that the case? I didn't miss anything? Yeah. And yeah, alright, and you just would pass it directly straight up to here. So like you would just say attrs or attributes if you want, vertex attributes. I don't think you can do it like directly here though, can you? I mean, it seems like you can, so that's good. And yeah, there you go. Next up, is there anything else? That's the buffers. Yeah, and I think right now you just gotta like set the buffers and yeah, just draw the right stuff. Yeah, I just set the index buffer, set the vertex buffer. We don't have any bind group for now. And these are just for debug. And finally just draw the indexed index count. And yeah. And finally here we could just have like an index count. View size. And the index count is too simply indices dot size or count, or what was it, len? Yeah. C out, index C out. Okay, no. Let's just say index len or index count. Fine. Let's say index count. Next up, we're gonna come to our render function. And after, well, here first of all in the draw, we're gonna draw the up to index count. Well, as U32, I think. Or we could just simply say that this is U32, and then make sure we say as U32 here, and you're good to go. Next up, you gotta make sure to render pass, set vertex buffer. The slot, well, the first buffer, and the buffer slice would be self dot vertex buffer. I guess maybe dot slice. And we're gonna just grab the whole buffer pretty much. And we're gonna do similar thing for the render pass dot set index buffer. And the buffer slice is like self dot index buffer dot slice the whole buffer again. And here I believe you tell it which type of the index format. Okay. In our case, currently we're just using 16. And that's all. That's that, right? And I believe that's all you need. But we have a little problem apparently. Vertex 36 extends beyond limit 24 imposed by the buffer install 0. Interesting. Did I miss something there? Let's see what the AI would say really quickly here. Let's see. So we don't waste time on this. Not sure what I'm missing out on here. Oh, yeah. Just a little. Gotta make sure that this is indices. Copy paste problem, but we still have some error. Oh yeah. So instead of draw, you gotta use the index draw, I think. Or what is it called? Yeah, draw indexed, apparently. And the base vertex is 0. Well, I mean, let's make this cube red. And yeah, this is what we got, but it's pretty hard to tell what's going on there. So we're gonna add our transform, I think. Sure. So let's grab back our transform here. So we're gonna add this uniform binding, and that means we're gonna need, to add the like a uniform buffer essentially with the binding and so on. Okay, so let's see how we're gonna do this. And in fact, let's see how they did it. There you go, generate matrix. So this is how you basically do the camera stuff, right? So generate matrix. I mean, you could just steal this function, in fact, really quickly here. Oh, there isn't Glam, no. We could look into GlamX right now, actually. Yeah, sure. In fact, I think GlamX have better camera stuff, in fact. Yeah, they do have a D camera, apparently. And you go either with RH or LH. In our case, it's probably RH. And then you got Proj or View. There is Proj, DirectX, Vulkan, or OpenGL. Strange. View. And the View. Okay, I see. So the Proj, I'm not entirely sure which one we're supposed to use for WGPU, but I would guess DirectX. Let's see. And we're gonna use perspective. Perspective. So there is perspective, infinite reverse. Interesting. Well, I guess let's just go with perspective then. So vertical FOV, the aspect ratio, the near and far. Well, for now, I'm just gonna like copy this exact thing here. And boom. And this is your projection matrix. There you go. Now here, add save cast to if. Okay, so apparently GlamX actually uses F64, I think. But we'll see about that. And here, next up, we're gonna grab our view. So our view is D camera RH view, and we have some few things here. Look at. So we either have like Affine 3, Matte 3, Quatch, like Quaternion, or Matte 4, depending on which you want. Good question. Well, I think I just want a Matte 4, please, for now at least. And we're gonna give it like the DVEC 3. And it's gonna be like F64s. So let's just copy this guy. But instead of F32, it's gonna be F64. What else? Well, I think we're just gonna go ahead and do the rest. VEC3 or DVEC3, is that the case? 0. And again, GlamX, DVEC3, Z. And boom. And finally, we're gonna say projection times view. And we're gonna go with DMAT 4. And yeah, and that's how you use GlamX apparently. Cool. And here, let's import this. Import it from F64. And that's your matrix. So that's basically your camera matrix essentially. And next, let's see where we grab that. Oh yeah, so we just create a uniform buffer with copy DST. And we give it the width divided by the height for the aspect ratio. And we have that as ref. And as reference F32, 16. Interesting. So, interesting. Well, we could do that, fine. Let's see. New before the shader module, fine, or whichever. Let's see what we got. So camera matrix, or camera matrix, yeah. Camera matrix. Well, let's call it something else, I guess. I mean, fine, let's call it matrix. I don't know what you call it. Let's see. And here we're gonna go with the width and height. Do we have width here? Yikes, no way. So let's just say window width, window height is equal to window dot inner height or inner size dot into, and here we're gonna go with the width divided by height. Well, instead of into, maybe we could just well, actually this should be a 64, okay. Maybe we could just say U32, U32. No. Expected 0 found 1. Really? Can we do this? No. But like how? Maybe we could do this then. And here we could say right now, go into. Okay, cool. Now that we got to our matrix, we're gonna create a uniform buffer. So the uniform buffer is, well, let's just say device create buffer init and buffer init descriptor. Okay. And here the contents. It's gonna be our matrix. I guess as ref. There you go. And the usage. So for the usage, we're gonna go with WGPU buffer usages uniform and WGPU buffer usages. Copy DST because we're gonna upload data to it. Now what's up with the contents here? Expected UH. I think we could just like cast bytemax slice, but let's see how they did it here. Yeah, there you go, bytemax cast slice. So yeah, there you go. And that works. And then we basically create a bind group. So a bind group is basically device create bind group. WGPU bind group descriptor. Okay, and expected wait, what? Oh, well, Let's remove that part. Set the missing fields, label none. And here the layout. The bind group layout. Where this is coming from? Wait, what? Wait. Bind group layout. Create bind group layout. So I gotta create that first before the bind group. Okay, sure. Create bind group layout. Bind group layout descriptor. Add the missing fields. And here the entries. What is the entries here? It's bind group layout entry. Got the binding 0. The visibility is GPU shader stages, and the transform would be visible in the vertex stage, and here the binding type would be uniform, I guess, or just a buffer too simply. Yeah, just a buffer. Good morning, Yo-Yo Man 3D. Welcome to the live stream. What's up, bro? And here we got the type. Well, the buffer takes in the type, which is binding type buffer. Well, WGPU binding type buffer. Oh, there's some other stuff. Wait, what the heck? No. Something strange going on here. Really? Expected buffer binding type. Is that the trick here or what? Kinda confused. Yeah, I think so. Bro, what? Really? Binding type, okay. No, wait. What? Buffer binding type uniform. Okay, there you go. So either uniform or storage. Then has dynamic offset, false, minimum binding size, none. I'm not sure about this one, but we'll see. Yeah, it is a nano. Type count none. What does this count though? Oh, the array count, I guess. Okay, maybe this is for arrays. Next is, well, we don't have any bind one currently, so that's good. Finally, the pipeline layout. I wonder if we gotta have the pipeline layout. I mean, I think so. Yeah, I think so. At this point. And now as we could create the bind group. And so the bind group is, you give it the bind group layout. And finally the entries. Here where you actually bind the resources. So the first one is bind group entry. Let's see. Add the missing fields, the binding 0, and the resource that we're gonna bind is binding resource buffer, obviously. And what this takes exactly. Oh, so just do this. A buffer binding. Okay, where's the bind group here? Oh, okay. So you just say as entire binding. Alright, sure. And there you go. And that's that. Now I guess you just gotta like use that bind group. Yep. So we gotta store them. There you go. Okay. Jorian199, welcome to the live stream. Yeah, WGPU is a bit verbose, kind of like Vulkan, honestly, to some degree. Especially with this bind group part, it's very, very verbose, even more than Vulkan, I think. Actually, not really. Vulkan have its own bullcrap too, but if you use the modern features in Vulkan, you wouldn't have to deal with that crap. Like in Vulkan 2, you gotta do with the scripture set layout and all sorts of weird crap, but yeah. Anyways, let's just add this. But this is kind of like just the initial setup, you know, nothing fancy, I guess. Later on, we could possibly investigate how we could do bindless, and it would be way easier. But for now, we're good. Alright, what are we gonna do next? Alright, so here you just basically bind the group. Yeah, I just set the bind group. Give it the index, I would guess 0. The bind group, which is our self.bind group. And the offsets, which is kind of like, I guess, 0. And this probably supposed to grab a reference, and let's see if that works. And yeah, we got a little error here. Whoops, I see. So no offsets there. And yeah, we're getting a black screen now. Interesting. Let's see what I would say we missed. a group and get in the black screen. Let's see. Let's see. So convert the 64-bit matrix to 32-bit F32 matrix. I see. So let's see how that would work exactly. So I guess just like that. There you go. And we got a cube. Nice. So basically the problem was that look at that cube, wait. It's just like squashed because I didn't update the camera aspect ratio yet. Okay. So the problem is that this camera matrix gives us a D match 4, which is basically a double matrix 4, which is like F64. But you could see as mat 4 to grab the F32 version. And yeah, now I gotta make sure to update this every time the resize happens. And where are we gonna do that? Well, obviously in the resize. Do they do the configure first or the... I mean, it doesn't really matter, but I'm just curious. Let's see. I would guess they're probably calling it reconfigure surface, no? Well, apparently they're calling it resize here, okay. Weird. Anyways, let's just see what we can do here. So just gonna paste that in there. We're gonna generate a new camera matrix. There's you're gonna say like self queue right buffer. And the buffer is self.uniform buffer. Oh wait, I didn't store it though. Wait, how? Oh yeah, because I'm binding it using the bind group. I see. And then the offset, which I would guess is probably 0. Yep. And then the data, which is basically ref, right? Oh well, cast slice as ref. Bytmark. Cast slice matrix as ref. So basically as ref turns that matrix into a slice of F32s of floats, 16 floats. Then the cast slice turns that, you know, that like F30 or like 16 floats into bytes essentially. And that's how it works essentially, but yeah. This function takes 3 parameters. Is there like another parameter or what? Oh, I think I probably missed 0 here. There you go. Now let's just make sure to store the uniform buffer too. There you go. And let's just add it here. And yeah, let's consider borrowing there. And apparently there's something else that we're missing here, I think. What is it? Okay, self.window. And that's that. And that should fix it. There you go. Now when you resize, it stays in the same aspect ratio because we're updating the uniform buffer with the right matrix. Sick. Well, what we're gonna work on next is, well, obviously we don't have a depth buffer just yet. That's important for a 3D cube. So I think we'll just add that. Okay. Well, they're actually not adding it here. Is that the case? Depth stencil attachment. Yeah, they're just setting it to none apparently here. Interesting. Weird. I mean, it's fine because yeah, they're just not using a depth stencil, I believe, here. Yep, they're not using it. Okay, let's find another example that uses it. Or should we just go straight up for the textured cube? There's no depth example there, huh? Cargo generate. How much time we've been, by the way, streaming? Okay, 3 hours. Yeah, so I think I'll just stop the stream here. Demonstrate so we don't make it very big, and so I can have some time to think about where we're gonna take this next. Yeah. Alright, so let's just, I think, commit this stuff. Cube, just that. Or should we add a texture next? Should we add a texture? Nah, texture is a bit more complex too, if you're gonna upload one. But yeah, alright, so let's just commit this stuff for now. Let's keep it under 3 hours actually. Fine. Commit. And I'm gonna like publish this into GitHub. So if anybody's following along, add an account. Okay, hold on a second. Add account, log in. There you go. All right. So public, and yeah, share. And boom. Let's just add a little license really quickly for anybody who really cares about that. Let's just go to MIT. Not the best licenses. Alright, so yeah, that was it guys for this stream. Tomorrow we'll continue. See you later. Goodbye everybody. And here's the link. So okay, so see you guys. See you later.